This is a speedboat, or as many of you would say, a blobby mess of plastic with the contours of a 3D benchy. But what can we learn from the speedboat and how can it help us to improve our printing quality without sacrificing speed? This and more you will find out in this video. Hey and welcome back to my channel. I'm Matt, the printing nerd, and today I want to share with you a simple and yet effective strategy for interactively enhancing the construction of your 3D printer. By following this strategy, you'll be able to make gradual improvements to your printer's performance, resulting in better print quality, higher print speeds, and a more reliable machine. So, without further ado, let's get started. To kick things off, I would like to share with you an example of my first 3D benchy I've printed on the new V100 1.1 construction. As you can see from the print, there are a few issues we need to address. So one of the biggest problems that stands out the most are the visible layer lines at the lower part of the print. So as I know this is an issue that many of us had in the past, I would like to ask you for your expert opinion on what could cause this problem. So stop this video, take a moment, maybe rewind it, and take a closer look at the lower part of the boat and think about what might cause this error. For my first assumption, I've looked at the side of the boat and noticed that the issue was more present on the side than on the front of the boat, making me think that it might be flow related since the sides were printed at a higher speed and therefore the flow was also higher than on the front of the boat where the tool head gets slower and where the issue is almost gone. So my guess was that there might be an issue with the nozzle, maybe partial clogged or not tightened properly, which both caused under extrusion. My second assumption was related to the temperature. When we look at the surface finish, we see that it's matte, making me think that maybe the temperature was too low, which could cause also under extrusion. Maybe there was an issue with the filament. Maybe it was too old, or it could be an issue with the temperature sensor or an issue with the configuration of the sensor. Maybe I used the wrong sensor profile in Clipper. So all of these issues might cause that the filament was printed at a too low temperature, which could cause this matte finish and also cause under extrusion. My next guess was a partial binding on a linear bearing on the y-axis. I printed this boat with a reasonable fast print speed for a new built machine, and I guess that maybe a rod might be bad or the tolerance of a linear bearing on the rod was too tight and caused binding, which might cause such a layer lines. And for my last guess, this one was also related to the y-axis. I thought I might have a loose bolt on the tool head, which causes that the tool head moved, and especially at higher accelerations, this layer lines might be caused by this loose bolt. To summarize, all of this is guesswork and it can make the process of troubleshooting issues frustrating and time consuming. What if I told you that there might be a more effective strategy that could save you time and help you to solve those issues quicker? Before we dive further into the strategy, we need to have a basic understanding of material science. When we are faced with physical or mechanical problems, we can break them down into a representation of stress and strain. To visualize this, let's have a look at the typical stress curve of a mechanical construction. On one axis, we have the strain that we put on our construction. In 3D printing, strain is a combination of speed, acceleration, the weight of the tool head, friction of the axis, friction of the belt, and other factors. The cumulative effect of these strains leads to stress in the structure, which is represented on the other axis. To gain a better understanding of the impact of stress and strain on a 3D printer construction, it's helpful to classify them into two areas. In the first area, stress and strain are directly proportional to each other. This means that the energy caused by the strain is transformed into stress on the object without causing any deformation of the material. This area is considered to be stable since the material properties remain predictable and reversible. It's important to note that while the material doesn't deform in this area, it still experiences stress, which can lead to failure over time. Moving into the second area, the strain on the object exceeds the limit of the stable range, causing multiple forms of stress to be created as a result of the energy transformation. It's not longer possible to define a relationship between stress and strain in this area, as the complexity of the energy transformation makes it difficult to analyze. Continuing to increase the strain leads to a critical point where the stress becomes too high for the construction to handle and it fails. In the context of 3D printing, this may manifest as a blocked linear bearing, a skipping motor, or a clogged nozzle. When it comes to achieving high-quality prints, there is a sweet spot where the best print results are obtained. In the past, this sweet spot was located at the end of the first area. For example, our goal was to make the construction of a printer as stiff as possible and use speeds and accelerations that the construction could handle. However, with the advancements in technology, we are now able to move the sweet spot further in the second area. Tools such as input shapers can measure the vibration of the construction and use algorithms to compensate for them, allowing for a more accurate description of the stress and strain relationship in this non-proportional field. Another example for a tool that works in the non-proportional area is pressure advance. In the past, there was a limit on extrusion speed due to the risk of blobbing and stringing when the pressure reaches a nonlinear level. However, with pressure advanced, we are now able to print at a strain point that is far beyond the first area by predicting the change of pressure in the print head and reducing it before blobbing happens, resulting in a higher quality print. Although being able to properly work in the nonlinear area leads to higher print speeds at a better quality, it also makes troubleshooting very challenging. So here comes the failure point into play. It plays a crucial role in various industries. For instance, in the automotive industry, every car design undergoes a crash test where it's driven into a wall to determine which part of the vehicle deforms the most and therefore represents the weakest point. By improving the design based on the results of the test, manufacturers can not only move the failure point further, but also expand the linear and nonlinear areas, which leads to a significant improvement in product quality and reliability. When calibrating and enhancing a 3D printer, we often rely on similar methodologies. For example, when determining the maximum volumetric flow for a given material and temperature, we increase the extrusion rate incrementally until the motor starts skipping. This skipping represents the failure point in our calibration process. However, even before the motor begins skipping, we can observe that the material flowing out of the nozzle starts curling. This curling indicates that we have entered the second area, where the strain of the extrusion causes multiple stresses, one of which results in the melted filament curling. Determining the maximum acceleration for a given speed is another example where failure point analysis can be helpful. To achieve this, we move the tool head through a series of big and small fast motion changes until the stress on the motion system reaches a critical level, causing a failure by blocking. Similar to the volumetric flow test, we can observe multiple stresses caused by the speed and acceleration, leading to skipped microsteps in the stepper motors. Therefore, even if the movement appears to be fine, stress still caused issues in this area. In summary, we have learned two principles that we can use to enhance the construction of our 3D printers. First, every moving mechanical construction behaves similar to the graph we have seen. There are always two areas, the linear and the nonlinear area, as well as the failure point. By moving the failure point up to the top right of the graph, we also increase the stress areas of the construction, resulting in a more reliable construction and creating more room for speed or quality improvements. A speedboat is the result of such a failure test. by disabling every parameter in the slicer that causes the printhead to slow down, such as retraction, minimum layer time, overhanging wall angle or small features, and increasing the maximum speed and acceleration, we push the printer to its limit, provoking a failure. If you want to learn more about it, I have already described it in a previous video, which I linked in the info card. In comparison to the opening question, analyzing the reason for a failure is quite simple. Most of the time it's obvious which stress caused the failure. So let's have a look at a couple of benches I've produced in the process of tuning my current D100 printer to see how to use these principles in practice. Let's have a look at the boat from the initial question of the beginning of this video. This boat was printed in about 23 minutes with moderate settings. I've used a maximum print speed of about 100 mm per second and an acceleration of about 5000 mm per second squared. For me it was important that I pushed the construction not as hard as possible because I knew that it was a new construction that might have a couple of issues that cause stress on the construction. So my goal was to keep the strain as low as possible, so I used very moderate settings for this print. So the boat was printed after I've done some basic tuning of the machine. Tuning like extruder calibration, pressure advanced, retraction calibration, and I also printed a couple of calibration cubes that actually looked pretty fine. So on the calibration cube I did not have this layer lines that you see here on the 3D bench. So my next step was to print a speedboat, and the idea behind that was that when I increased the speed and the acceleration to a maximum, the issue that caused these layer lines might cause a print fail, and by analyzing the print fail, it might give me a clue why these layer lines happen. So I loaded the speedboat profile, I limited the maximum acceleration to 20k and the maximum speed to 300 mm per second to be on the safer side and not damage the construction. And after I sliced the model, I got this little cutie. As you can see, the print failed. And when we compare both models, you can see that it failed at the position where the stress on the finished model was at its highest peak. But I have to say that all my theories that I shared with you before, all of them were wrong. So the issue that happened here was that the bolt was ripped off from the print bed by the tool head because it crashed into it. And it crashed into it because the print bed was not longer moving moving down on the z-axis. And it was not able to move down on the z-axis because it locked itself at the place where it was not able to recover anymore. So I've checked the construction and I found out that the left lead screw was a tiny bit bent, and after I changed it and after I checked also that there is enough play at both lead screws and at the two linear bearings on the z-axis, I reassembled the printer and I was able to print this little beauty. This is the speedboat I printed at 20k acceleration. So as you can see, there are almost no layer lines at the lower part of the boat. So for comparison, let's have a look here. As you can see, there are multiple layer lines, and here the layer structure is, for a speedboat, it's almost perfect. So this made me pretty excited to reprint this one now that the construction is tuned. And so I did, and I got this boat. As you can see, here for comparison, the structure of the layer lines of the lower part of the boat, it is so much better. There are almost no issues on the side of the boat, and here's a small issue, but to be honest, this is much better. Besides the issue here on the front. From my experience, I knew how to deal with that dent in the front of the boat, so I've changed a couple of slicer settings, I reprinted that boat, and here we go. The dent is still there. So I changed another slicer settings, reprinted the boat again, and it got a bit smaller, but it was still there. I repeated the process for a fourth time, and it was still there. I repeated it for a fifth time, I repeated it for a sixth time, and a seventh time, and actually now things got very frustrating because I was not able to get rid of this dent. So I stopped guessing and went back to my speedboat strategy. I've printed a couple of speedboats increasing the speed and the acceleration step by step, and I ended with this beauty. This speedboat was printed at a speed of about 320 millimeters per second at an acceleration of 35 km. Going further was not possible because when I increased the speed or the acceleration, the x-axis blocked. So I've checked the bearings on the toolhead carriage, and I noticed a little bit of scratching on one of the linear bearings. So I changed it, I reassembled everything, and I printed this nice speedboat. So when you look at both of them, they look pretty similar, but the one was printed at a speed of 320 millimeters and the other one was printed at 450 millimeters. One was printed at an acceleration of 35 km, the other one was printed at an acceleration of 85 km. So this is another big improvement of the construction, and by the way, this speedboat finished at 5 minutes and 40 seconds. So I went further and I reiterated a couple of times more, and I ended with another 3 boats. So let's start with the first one. This one I would call a perfect speedboat, and I say perfect in quotation marks since there are many smaller mistakes that make this boat look a bit messy, but for comparison, let's have a look at the boat that finished in 5 minutes 30 for comparison, and look at that. It looks much worse because this one was printed without retraction and with a minimum layer time of 0 seconds, causing the chimney to melt. So, but let's go a bit into detail. This one was printed at a speed of 600 millimeters per second at an acceleration of 60 km. I re-enabled retraction with a very low value so that it's not hurting the printing performance too much, but it gets rid of about 80% of the stringing. And I also reactivated minimum layer time so that the cooling of the upper part, especially of the chimney, gets a bit better, causing the chimney not to melt, and it only hurts the printing time by a little bit. So after all, the print finished in 5 minutes 27 seconds, which is my new personal fastest speedboat record on the 100. I will talk a bit more about it in a future video, and about changes on the construction and changes on the parts that I've made to improve the performance of the printer as well. So if you don't want to miss that episode, hit the subscribe button and activate the bell. And by the way, I'm almost finished with the alpha phase of my next printer release. And as soon as the printer goes into beta, I will share the construction with all of my Patreon. And currently, I guess that this will be end of May. So if you like to get access to these beta parts, consider becoming a Patreon. So for all others and that want to support me, do this by hitting the like button, write a nice comment under this video. Maybe you could tell me what you've learned from this video, and maybe we can talk a bit about parts that you want to go into a deep dive in an upcoming video. Well, write about it in the comments. And another announcement that I want to make is that we will be part of the Maker Faire 2023 in Hanover, which means we will show our 100 printer there in our booth, and we will do live printing, we will print speedboats, and also we will try to break our current speedboat record. So if you like to meet us, if you want to know more about the team behind the printer, or maybe if you like to see a printer explode while trying to create a speed benchy, well, come to Maker Faire, visit our booth and have a talk with us. And by the way, if you are one of those who is building a 100 printer by yourself and you would like to participate, I want to invite you to be part of our booth with your printer. My goal is that we have about 10 to 15 custom designed printers designed by the community standing at our booth and building an army of fast printing machines. Oh, that would be great. So if you like to participate, contact me at Discord. And last but not least, well, I plan to be able to release the next version of the printer at Maker Faire in Hanover. So if you like to see the new features of the printer first, live in action, come to Maker Faire Hanover. And if not, I will release the blueprints, the step files, and everything you need to create a new version at 21st of August. This is one day after Maker Faire. Okay, let's go back to the speedboats. And this time I want to show you what I would consider to be a perfect benchy. So this one was printed with 2 walls and 3 top and bottom layers, and at a layer height of 0.2 millimeters with 15% of infill. The speeds were fast, but not crazy fast. I've printed the infills at about 300 millimeters per second, outer walls at 100 millimeters per second, and inner walls at 160 millimeters per second. All the accelerations were between 15K for the infills and 5K for the outer perimeters. This boat finished at about 16 minutes and 21 seconds, which was very close to my goal of 15 minutes. So in comparison to this, here is my unperfect benchy. This benchy has also 2 walls, 3 top and bottom layers. It has the same infill, but this time it was printed at 0.16 millimeter layer height. Here I went a bit faster at 400 millimeters per second infill, 135 millimeters outer walls, and 200 millimeters for the inner walls and for the top and bottom layers. The accelerations that I used were between 30K and 10K. This one finished at 11 minutes and 41 seconds, but as you can see, there are a couple of artifacts that might be a bit problematic for some of you. Starting here at the back, here you can see them. There are little vibrational artifacts on the back part of the boat, and also here at the back part of the upper part. This vibration lines caused by the high acceleration the printer is moving, and even if the input shaper was calibrated, it was not able to compensate this vibration because the algorithm Clipper uses compensates only one wave of vibration, and these artifacts were caused by the second or maybe also by the third wave. And since the algorithms are only focused on one wave to compensate, we have artifact lines that are not really bad, but they are there. But this is something, fortunately, that could be fixed or could be improved in a future version of Clipper. So it might happen that these lines disappear in the future, when we get a Clipper update. Another issue you see is here at the front of the benchy. As you can see, at the area where the printhead slowed down, the color of the printed material changed. This is because filament manufacturers add chemicals into their filament that make the surface finish glossy. But these chemicals need a bit of time and the right temperature to react with the filament, time that they don't have when you print very fast. By the way, if you looked at those polished pictures of high quality, high-speed benchlys from manufacturers like, for example, Creality, Bamboo or Kidi, you might notice that they all use matte filament. And they use it because when you use matte filament, they don't need these chemicals to be glossy, and therefore they're not causing this issue. So, but I believe that filament manufacturers might change their formula, so they could adjust it to have different chemicals that make the filament glossy, maybe chemicals that don't need as high temperatures or that react faster, so that they could be used at a high-speed environment like the one we use at the D100. So I'm not sure if maybe there are already filament manufacturers out there that already have adapted their formula. So if you know a manufacturer that does not tend to lose their glossiness at higher speed, feel free to give me a tip in the comments. And yeah, I really would try another filament brand to maybe get rid of this this color changes here on my benchy, and improve the quality of the benchy even more. So that's it for today. If you learned something new, I would be happy if you press the like button, subscribe to my channel and write a kind comment under this video. As always, stay tuned for new content, and now get out of here.